Okay, good morning, good afternoon, good evening, everyone. Welcome to this week's ARMA Future Leader webinar. Our speaker today is Professor Renato Macciotta. Sorry, I may have said that
That was really
absolutely
good,
butchered.
actually. No, that was really good. That was really
Thank
good.
you. He's an associate professor in the Department of Civil and Environmental Engineering at the University of Alberta in Edmonton, in Canada. He obtained his bachelor's in civil engineering at the Catholic University of Peru and his PhD from University of Alberta in geotechnical engineering. He has 20 years of practical experience and 15 years of research experience in both civil and mining geotechnical projects in the fields of site characterization, slope stability assessments, remote monitoring, hazard risk assessment, and various other aspects of slope stability. He's very active in research and industrial projects and is published in over 70 peer-reviewed journal articles. So thank you so much for coming and making it. Looking forward to hearing your presentation. And please, the floor is yours.
Thank you, Bing, and thank you very much for the invitation. It's actually an honor to be here speaking to you, and that you thought of myself for giving this presentation. I really, really appreciate it. So yes, as Bing was saying, I'm a civil engineer, and my world has taken me to dealing with geomechanical problems and civil and mining, and also dealing with other types of mining structures, such as the tailing dams and waste rock dumps, as well as natural hazards for the civil world, right? Typically linear infrastructure. So I do quite a bit of stuff with the railways here in Canada and Alberta transportation. What I'm gonna talk to you today is about some work that we started doing with some of the LOP members. The LOP is a large open pit project, and that is a consortium of large open pit operators that includes Newcrest and BHP and the Rio Tintos and Vale and many others. And what they're looking at is research and practice and initiatives to optimize pit operations and safe pit operations, right? So this work came to be as such. But before I get into the details of what I wanted to share with you today, as we typically do in mining and many other industries, I want to start with a safety share, okay? And that's because this is exactly what we do every time we meet in mining, right? In the safety share I have for you today, I've called it Fit for Duty, and it is a personal perspective. What you see on the upper left-hand side, that's the Raul Rojas open pit, and this is in the Andes of Peru. And the pit is, or the crest of the pit is at about 4,000 meters above sea level. Some sections probably 4,100 meters above sea level, right? And the task at the time, and I was a young engineer at the time, was to go and do a pit inspection, right? It was part of an overall mining inspection, so it was just one of the tasks. So we arrived there from the coast, and we had to do the inspection on that day. And it was me in the truck with another engineer. And you can imagine that your body doesn't like it too much when you're moving from 0 meters above sea level to 4,000 meters above sea level, and you are supposed to start working, right? So of course I was not feeling great, slight headache, and that's because of the relative shortage of oxygen when you compare both elevations. But I was still okay to go out and do my inspection. This other engineer said was feeling not very well, right? So we were driving on the truck and we were stopping at certain locations to do the inspection, and I was stepping out of the truck, doing my visual inspection, taking notes. But this engineer was just staying in the truck. And then as a young, naive engineer, I thought to myself, well, we are already here. We are being paid to be here. So we should do the work, right? We should get it done. So I inappropriately started judging my colleagues, saying like, come on, we should put a little bit more effort. Later, I matured and I realized through lessons, well, you need to make sure that you are fit for work, right? And it was until a couple of years ago that I had to do another repeat inspection. And this was here in Saskatchewan. And it's an in-pit tailing storage facility. And I had to go there. I had to drive around, right? Step out of the truck, do my visual inspections, just like I did so many years ago in the Raul Rojas pit. And when I am stepping into the truck after just to go to the site or just at the site, I pulled my back really bad to the extent that I could still do the inspection, but not going out of the truck. I had to do the inspection sitting in the truck. Just like that other engineer so many years ago had to do. And that's when I already knew because of courses, because of training, but that's when it hit hard, right? You don't know how the other person is feeling, right? We have to accommodate what our colleagues judge as being fit for work or not being fit for work, right? We always have to evaluate ourselves before the day and make sure that we are not just physically fit for work, but also mentally fit for work. Because if we're not, then we are increasing the likelihoods of a mishap, of an incident from occurring. Okay, so that's the safety share for today. I hope you took the lesson, and I hope it was it's a free lesson. I had to suffer my back that day to learn the lesson by heart, but I hope you take that home today as well as what I'm gonna tell next. For this lecture, some of the contents will start with the context of open pit wall design. What is it that we're trying to do with these designs? I'm going to talk about uncertainty and design reliability. And then I'm going to talk about the specific work we did with the LOP on design acceptance criteria that considers that design reliability. All right. So let's talk about the context. When we talk about open pit slope design, we're typically talking about the design of these slopes at 3 scales, right? And we're talking about the bench scale. We're talking about interramps and overall. What's a bench? A bench is just a slope that is typically 8 to 15 meters in height, although some operations can have double benches, but let's not dwell on that. And then there's a space in between the next bench. And their main purpose is to be a control for rockfall. Okay, so to try to catch any rockfall, any failure that would occur at the bench scale and prevent it from reaching the working floor, the working level. Okay, it has, depending on the location, other objectives, such as help you manage surface water, right? But in essence, for most part, it has to control rock. Then the next scale of it, it's the interramp scale. And the interramp scale, as its name says it, is that slope in between ramps. Other wording for it is multi-bench scale, right? So we're talking about 3, 5, right, benches, maybe more in between ramps. And they will have a shallower angle as compared to the bench scale, because you do not only have the slope of the bench, you also have the spacing of the bench and even the spacing of the ramp, and that starts giving that slope at the interramp scale, or that inclination of the slope and the interramp scale. And then we also have the overall slope, right? And the overall slope is even less steep, even flatter, because then we have to take under consideration all the ramps that will be on that wall. Now, that is very fitting, because as you will know, there will be a certain scale of structure and structural control at the bench level. And then the rock mass itself at the bench level, it starts getting closer to what you would get from a laboratory rock strength, because that's how you can treat it in between those discontinuities. But when you move to the interramp scale, and even more at the overall scale, the rock mass starts taking on more of the smaller scale joint systems, right? So that strength degrades. And then you also have that very important role of the larger scale fractures. And therefore, the overall slope that can be stable starts getting flat. Today, we're not going to focus on the bench scale. We're going to talk more about interramp and the overall scale. And these slopes are evaluated through slope models that we check from slope stability. And it is very common to adopt empirical techniques at the beginning, right? So charts, but then move towards two-dimensional limit equilibrium models. That is very typical. Even in some operations, for some advanced stage of these operations, they will still use two-dimensional limit equilibrium for some of the design phases. It is only when you have failures that then the operations will decide, you know what, we can learn a lot from this failure, or maybe the failures are starting to get closer to the not acceptability, and they deploy three-dimensional tools and typically numerical simulations so that they can do back analysis, get a better understanding of what's going on, and then improve those designs. And lately, that has been implemented to optimize these designs as we transition in open pit mining from a prescriptive approach in which factors of safety dominate, probabilities of failure from the calculations of a slope stability dominate, to a more performance-based approach. What do we know about the behavior of the slope? Can we monitor it? Is monitoring telling us that the performance is adequate, right? But the role of modeling and the role of calculating these still is prevalent in industry, and it's still a very key role in the initial stages, right? So how do we get to a slope stability analysis? So what you see on the right-hand side, I've borrowed it from the design workflow in the LOP guidelines for slope stability, for open pit slope design. That was 2009. And of course, you have field data that then gets interpreted into geological models, structural models, rock mass models and characteristics, and for sure, hydrogeology. And then all of that information has to feed the engineer with what are the potential deformation and failure mechanisms, right? Because that is going to then rule what assumptions and what simplifications you need to make from the geological model, structural model, rock mass model, hydrogeological model, so that you can build a geotechnical model that it is practicable for your analysis, but that captures the potential deformation modes, the potential failure modes, right? And based on that, you start building your domains, strengths, structures for that model, and then design sections, etc. And that's how you reach that level where you start carrying out the stability analysis, right? And now we start the stability analysis, I said, are governed by empiricism at the initial stages to give you a ballpark of what's going to be the geometry, and then you move towards limit equilibrium analysis, typically in 2D. And when you find an area that needs to be prioritized, that needs a little bit more scrutinuity, a little bit more work, or if you have some failures, then you move towards numerical techniques to calculate stress reduction factors in 2D or 3D, right? Now, of course, to be able to decide if a slope is safe enough or not, we need criteria. And there's been criteria proposed in the past. Many people has proposed criteria in the past. But that was summarized and somewhat synthesized in those 2009 guidelines by Rita and Stacy. And that was based on all that published data, experience from them both, and the people that were involved in those discussions. And it was part of the LOP. So you can understand that many representatives of the operations were present in that meetings. And what you see here in that table is what they came up with, right? And you have values of factors of safety, values of probabilities of failure. For example, if we look at the slope scale for overall, and very wisely, they are giving you guidance depending on the consequence of the failure, right? If the consequence of the failure is minor, there's not going to be anyone working on that side. The slope is near final, or there's no mineral associated with that slope because you've already taken it, everything you wanted to take. There's no interramps going through there, no structures, no people exposed, and it's a low risk. You can be a little bit more aggressive with your design. But if there's a good ore body there that you want to extract, or if you have a key ramp going through that slope, or if for whatever reason you have your main crusher at the crest or at the toe of that slope, then it's a very high risk. So you cannot be as aggressive with your design, right? So they recognized that, and they proposed factors of safety and probabilities of failure, target factors of safety and target probabilities of failure, right? Now, these numbers are very important because, as you can see on the figure on the right-hand side, just a few degrees in the slope of that angle can entail a lot of money because you're either recovering less or more ore, right? Or you are requiring to excavate more to get that ore. So a lot more waste. That means a lot more effort in the excavation. That means more footprint for your waste rock dumps, right? The one thing that this table does not have in there, they wrote it down conceptually, but they didn't include here, was the level of reliability that you have in your models. Because not all factors of safety, and I'll tell you, not all probabilities of failure are the same, right? If you have a couple drill holes for mineralogy assessment and you base your whole model on that, it's very different than if you have a bunch of drill holes for geomechanical purposes, together with in situ tests and laboratory tests, together with monitoring of the previous phase and back analysis of that monitoring and what the behavior of the slope was, right? Those two calculations with those two models are going to be very different. One is going to have very low reliability. You're going to have a very, very low confidence on those numbers. The other one, you're going to feel much better about, right? So that's what was not captured here, that uncertainty associated with some of these analyses. So what is uncertainty? What is design reliability? I'm going to show you, I call it a working table. And because I use it, I've presented a couple times. I have not invented it. I've borrowed it, and I Frankenstein it from other people, and mostly from Dr. Morgenstern's 1995, where he talked about categories of uncertainty, and from Stefan et al. In 2008, where he talked about sources of uncertainty. And then this is what I put together. On the left-hand side, what I've done is put this typical stage, and this includes like design from conceptual towards operations, towards design for closure, etc. Like when I talk design during operations, I'm talking about subsequent phases of an open pit excavation. I've put these as well for tailing storage facilities and for natural hazards. So for tailings, for example, if you need to do subsequent raises of your tailing dam, then this is applicable as well through operations. Then uncertainties through the implementation and operation, and uncertainties through closure, implementation, and post-closure, right? So for each of these stages, we have sources of uncertainty, and the components include the geological setting, rock mass, soil, rock structures, tailings, right? We have the loading and unloading for performance analysis. And for each component, we'll have certain sources. So when we are talking about the geological setting, what are the possible sources of uncertainty? Topography, not so much, but there's some source there. But for sure, the geomorphology. If you are in an area like some of the pits in the Andes in Chile, for example, very, very thick layers of materials that were carried by really ancient rivers, and then they got really, really solidified there, right? So uncertainties with that geomorphology, uncertainties associated with lithology, and even with weathering and hydrothermal alteration, for example. For sure, uncertainties associated with the structure, right? I mean, and particularly when we always draw large scales, or I should say large fractures as planar features, and we know they're not. What's the uncertainty associated with that? We have a plane that it's a structure that varies between 2 meters and 6 meters in width, but we're drawing it as a plane. And we know that it is not flat. And we've interpreted that plane on the basis of, I don't know, 3 boreholes, 5 boreholes if you want, right? So the uncertainty associated with that. And in terms of materials, for example, rock mass, soils, etc., the strength, their behavior, what behavioral model is going to be closer to what is going to be mobilized in the field for the particular mechanisms of the formation in this pit, right? Hydraulic conductivity, the scales of hydraulic conductivity. Does the hydraulic conductivity in the matrix matter for this particular site? Maybe not. It's hard rock, so everything's going to be through the joint systems and through the fractures. Maybe it's weak clay rock, and maybe how it responds to unloading is going to be a critical aspect for it, right? Maybe we're going to have delayed failures because of that response, and then equilibration of the pore water pressure within the matrix. I don't know, right? So all of those are uncertainties we need to think about. In terms of loading, that in situ stresses, pore pressure, but particularly extreme events. I have here seismic. Seismic is for many structures. We're yet to see a large open pit failure after that corresponds to a large seismic event. But how about weather events, right? How about extreme weather events? What we understood as a 1 in 1,000 year return period event, is it now a 1 in 100 period, in 100 year? So, and then we move towards the categories of uncertainty. And this is a very interesting aspect. And there are many, many categorizations of uncertainty. This is the one that I work with, that Dr. Morgenstern put forward, because in my mind is the easiest to understand. You can work with another one if you want. And this talks about parameter uncertainty. That's easy to understand, right? It's the scatter in the values. Do I have an outlier here, an outlier there? If you start doing a bunch of UCS tests for a particular lithology, right, just for a unit of lithology, are you always going to get 210 MPa for that UCS? Are you always going to get 30 MPa for that weaker rock, for that UCS? No. For the harder one, you're going to get 190, 250, 195, 205, et cetera, et cetera. So there's a scatter. So that's parameter uncertainty, and it can be because of natural variability, but it can also be because of sampling bias. It can be because of testing bias. It can be some scatter by the testing technique, the person that is doing the test, etc. The other one is the epistemic uncertainty or model uncertainty. That's very interesting, and that talks about uncertainty with what it is that we know. How do we understand the behavior of materials? It also has to do, when I talk about model uncertainty, with how we went through the assumptions to do that simplified model, right? So it's an uncertainty at a higher level, more difficult to quantify. Actually, can we quantify it, right? That's in the forefront of research. And the other type of uncertainty is what I call here decision and operational uncertainty, what it used to be called human error, right? And that has to do with the decisions we make. The decisions we make, for example, through the definition and interpretation of these geological structural models. How do we do the interpretation? There can be error from practitioners in there, but also decisions we make during the analysis and interpretation of the analysis results, and decisions we make with regards to implementation and interpretation of monitoring. So that's a big one, okay? And that's a very difficult to deal with. We're not going to talk about that in detail in this presentation. Just know that that's why we have our system managed, our safety management systems, our design management systems. That's why we have peer reviews. That's why we have then senior reviews. That's why we have then external audits, technical audits. That's why we have then the external review boards. Okay, all those layers of protection are meant to reduce human uncertainty in this workflow. All right. Parameter uncertainty, of course, affects where we're doing the stability analysis. Epistemic uncertainty when we're doing the interpretation of those models, converting them into geotechnical models, et cetera, et cetera. Now, we've become really good at dealing with parameter uncertainty, right? So we have a slope, as you can see there, very simple on the left-hand side. And let's say we want to understand what the uncertainty parameters is giving us. So instead of going for a factor of safety, we might decide to go for a probability of failure. How do we do that? Some of you here are probably experts on this. Some of you might have heard of this, right? So I'm briefly going to share with you how this is done. You have your model here, your slope, your units. You can add structure if you want. It's typically done with limited equilibrium because it's easier, but you can also do it with numerical models. It just requires a bit more effort. And then instead of providing your model with with an estimate of the parameters, you provide your model with a distribution, with a probability density function of the parameters. So if you have a, let's talk about in more Coulomb, which is easier to understand, right? If we talk about a friction angle, instead of giving it 35, you give it a probability density function that goes, say, from 30 to 37. Okay, and then there's a number of ways of doing this. You can use the first order, second moment type of techniques, and you can use point estimate type of techniques. There's others, and what they do is that they take certain values of those parameters based on the probability density function. They do the stability calculations there, and then assuming normal distributions, they can give you a calculation or an estimate of your probability of failure. Those are very, those are, let's call them older techniques, but that are still very relevant. For example, if you want to do this using a numerical simulation, the numerical simulation is going to give you a better approximation than a limited equilibrium model, of course, trying to match what's going on in the field. But then you need these other simplifications, right, to calculate your probability of failure. If you do a limited equilibrium model, then you can use another technique, which is the Monte Carlo type simulation, where you just input your probability density function. It runs a whole bunch of scenarios, and it gives you the result in the form of a probability density function of the calculated factors of safety. And then the area under the curve that is below 1, that gives you the probability that the slope is going to fail. Okay? That's how that is dealt with. Relatively easy. When we go into epistemic uncertainty, however, things get a little bit more difficult. And conceptually, we understand that if you have parameter uncertainty, you can calculate based on your on your limit equilibrium or your numerical, you can calculate a distribution of possible factors of safety, which will give you a calculated probability of failure. And what epistemic uncertainty is doing, it's actually making that distribution a little bit wider. Now, this is very conceptual. Why is that? Because if the epistemic uncertainty is associated, and this is very important, okay? So just wake up for this part. If the epistemic uncertainty is associated with the possibility of different failure modes, then if you run for those two failure modes a limit equilibrium, the distribution of the factors of safety, they can be skewed, they can be moved. And therefore, adding epistemic uncertainty to this could result in bimodal distributions of that factor of safety. But the concept still holds. What epistemic uncertainty is doing is increasing that probability of failure calculation. It's increasing that distribution. Okay? We've done some research. I'm not going to show it to you here, but we've been able to capture two different failure modes by doing these type of exercises, and we are seeing those bimodal distributions, not because something's wrong with the calculation, but because depending on the buildup of the model to address two potential failure modes, the results of factors of safety, the distribution of factors of safety, doesn't have to match and be centralized in the same location. So you start getting these bimodal distributions. With bimodal distributions, I mean not a nice distribution with a peak here, but something that gives you perhaps two peaks. Okay. Now, this was recognized as well early on when we were doing quantitative risk assessments of slopes. And this is a very important concept because when we run a limit equilibrium or a numerical technique and we go do all the effort to calculate a probability of failure, typically people have been thinking that, okay, I take that probability of failure as the actual probability that the slope is going to fail, and I can use that for a quantitative risk assessment. That's not really the case, right? Because in that POF, that probability of failure out of a stochastic analysis, right? It's just that, right? You are not accounting for other sources of uncertainty, such as potential for implementation uncertainty. What if they overmine? Or unforeseen geological conditions, or unexpected high water tables, or poor blasting, or extraordinary events like the one in 1,000 year coming in 100 in the next couple of years, right? So that has been recognized, and that probability of failure has to be, not calibrated but weighted, like they did here at Terbrugge et al., to try to find that real probability that the slope is going to fail. So that is what epistemic uncertainty is giving us. Now, how do we reduce that epistemic uncertainty? How that epistemic uncertainty is reduced? Well, as we increase the effort in engineering at the initial levels, right? Rather than using a couple boreholes for mineralogy assessments, we actually have our geotechnical boreholes. We actually have our in-situ testing. We actually have our laboratory tests. But then when we start implementing the design, we are doing the excavation, and we can monitor the excavation. And then we can do numerical back analysis of the excavation, and we can understand what's going on. What are the mechanisms leading to that, the formation we're measuring, right? And that starts confirming or updating our geotechnical models and our understanding of the behavior of that material. What are we reducing there? We're reducing the epistemic uncertainty. Yes, a back analysis reduces the parameter uncertainty as well. And that's what we've been taught. That's the first thing that comes to mind when we think about back analysis. Oh, beautiful, I'm gonna nail down the parameter. Yes, you're gonna nail down a parameter. But more importantly, you're gonna be reducing that epistemic uncertainty. You're gonna be more confident about what's going on with that slope in terms of mechanisms, right? So we're good with parameter uncertainty, epistemic uncertainty, increased efforts, and back analysis and performance, right? But then the question is, how much effort? What does it mean engineering effort? What does it mean a good level of engineering effort, right? And there's been work done in this space in the past. What you see here on the lower left-hand side is a work that published Meyerhoff in the 1970s. And what Meyerhoff did is that he gathered information from a lot of geotechnical structures, and he looked at estimating based on available data, how many structures had been designed and built, and how many structures had actually failed, and what were the typical factors of safety. And he was able to plot here, right? For example, this E is the calculation, his calculation of that relative failure rate, and he plotted it in terms of probability of failure. But this is real probability. This is not calculated stochastic. Okay? This is the real likelihood that something's gonna fail. And then against the typical factors of safety used, where E was earthworks, so embankments. So embankments typically with a factor of safety of 1.5 had this rate of failure. For retaining structures, right, retaining walls, typical factors of safety at the time of 2, these rates of failure. For foundations, typically these factors of safety at the time, and typically these rates of failure. And then what Silva et al. Did, and based on some work that Lamb had done some years before, is that they went into a number of case studies looking at the engineering effort in terms of the site investigation, models used for calculations and analysis, and then monitoring how robust the implementation was, QA, QC actually matching what the project requirements were, etc. And then they looked at that ratio of failure. So again, this probability of failure is now annualized, and it means really the likelihood that something's going to go wrong. And then they draw these lines, right, for the best structures, like very robust engineering, very robust implementation and monitoring, and the poor structures, right? The advantage of this one is that then they gave guidance of what best looks like, what poor look like. Now, caveat, some people have used this to map where they are in this table, their factor of safety, and try to back calculate a probability of failure. I don't think that was the intent, and be careful because this is an aggregation of many case studies. So it's not taking under consideration the particularities of your case study. So what this table is really good at is, where are you at? What does your factor of safety is going to mean in terms of relative performance? So therefore, where should you go to meet your expected goals for that structure? All right. Now, based on this work, we decided to leverage all that knowledge into making open pit design a little bit more efficient. And this actually started with some work that Rio Tinto's Kennecott Bingham Canyon mine had done. And that was done following increased scrutiny of open pit slopes after the 2013 Manifest failure that you have probably heard of, right? That large Bingham pit failure. And the work they did led to a double entry matrix of design reliability and consequence for defining target factor of safety. So what they did is that here on the upper hand side, you see that there's different levels of consequence, just like the 2009 guidance had. But here, instead of giving you the same numbers like they would give you in the 2009, they also weighted what is the reliability, how are you feeling about your design, your analysis, right? Where when you have very, very high confidence in your models because you've done back analysis and you really understand your pit, you can go for lower factors of safety compared when you have a relatively low reliability in those models. You have to be a little bit more cautious, right? That's what they developed. And that's when we, the University of Alberta, got involved with the LOP and Rio Tinto to try to put a little bit more context, to make it a little bit more systematic. And we got a bunch of case studies from industry, and we plotted that had calculated factors of safety and calculated probabilities of failure. And we plotted them in that space of factor of safety and probability of failure. And those are all these dots you see here. In what you see in the colors are the guidance provided by the 2009 guidelines from the LOP. And as you can see, some of them fit that guidance, but a lot of them, they don't. And when we talk to these operators, they say like, well, sometimes we're very nervous or we have an extremely critical structure, so we go with very higher factor of safety. And sometimes we're so confident on how this thing is going to behave that we pretty much just do a performance-based design. We don't even calculate much factors of safety. And we're happy with the rate of failures that we're getting. Because, and this is something I should have said earlier, an open pit that has no failures is a very costly open pit. There's a volume of failure that open pits tolerate in order to make it economic. And that's a balance between the cost of cleaning it up and maybe diluting some ore and the costs of making it steeper or shallower, etc. Okay? But as long as it is a safe operation. And how do they achieve safe operations? By monitoring and trigger action plans. So they can allow volumes of material to come down, but they have to be always monitoring, and they have to have robust tarps in order to mobilize equipment and people out of there. Okay, so with that, they can make steeper slopes and optimize the economics of the operation. So when we saw this, it was very familiar to us because, as you can see, it starts looking to like those two pieces of work that we showed you, right? Where we have the same sort of spaces. These lines correspond to unique correlations between factor of safety and probability of failure, right? And then we had that understanding of the poor structures and the best structures, right? So we started looking at its consistency. We started mapping it. And then the second question was like, okay, if we can leverage this context, right, to be able to know, to be able to pair that reliability in our models with what would be adequate factors of safety and probabilities of failure through this work that was done before, we need to understand what's the relationship between factor of safety and probability of failure. We know it's within this range. What is the actual correlation? So we just go back to our statistics course, and we know what a probability of failure is for a slope analysis, the area behind the curve for factors of safety lower than 1. We also know that this is a probability density function, and then this is the mean value here, centralized, right? Then if I have less uncertainty and a lower factor of safety, because it's less uncertain, I could end up with lower probability of failure. But if I have like the blue line there, like the blue distribution, but in the red distribution, I have a higher factor of safety, but it's so uncertain that the probability of failure, so that area, it's actually larger, right? So two different factors of safety for two different models doesn't really necessarily mean safer if for the higher factor of safety. But what is that relationship between factor of safety and probability of failure? That's done through the coefficient of variation. And what's the coefficient of variation? It's just normalizing the spread of the curve, the width of the curve. And how do we quantify the width of the curve? With the standard deviation, okay? So if we want to know what's that relationship, what's that width, what that spread of the curve in normalized terms so that we can compare apples to apples, we use the coefficient of variation, which is just normalizing that standard deviation to the mean value. So what you have here, standard deviation over the mean, okay? So now when we come here and we do a little bit of math, on the left-hand side, we see that each of these lines, the dark line, the black line, the green line, the gray line, etc., each of those solid lines mean a unique relationship between factor of safety and probability of failure for a given coefficient of variation. So if you have a given coefficient of variation, so that's how spread that function is, right? Normalized. If you have a given coefficient of variation, for a factor of safety, you can know what your probability of failure is. And that spread gives you the reliability in your analysis. So a lot of spread, like this brown line, the coefficient of variation 0.35, is less reliable, right? I shouldn't say less reliable. You have less confidence, right? You have less, your gut feeling is a little bit more unease compared to a model that has a very low coefficient of variation, right? Less variability. And when we mapped that to our case studies, we saw that it matched pretty well what Silva et al. Had proposed with the levels of engineering. So what did that mean? It meant that epistemic uncertainty at the beginning of an analysis, or when you have low probabilities or low information, you are dealing with a much wider distribution. We were dealing with much increased uncertainty, and therefore you have to target higher factors of safety. When you start getting knowledge of those slopes because of increased effort in your engineering, or because of you are already operating and you're getting that knowledge of how the walls are performing, then you have less spread in that knowledge, and therefore you can target lower factors of safety. Okay. And so we did a little bit of a review because we wanted to make sure that we wanted to make sure that we were not this some thought had been in the past about this, right? This knowledge. And we found that in other industry, there had been some research done in understanding levels of risk, not just as the probabilities and the consequences, but also as the level of knowledge. So we were moving away from that tolerability as being, okay, what's the likelihood, what's the consequence, but also, okay, what's the likelihood, what's the consequence, but also, how much do you know about the behavior of this system when you're calculating your likelihood and you're calculating your consequence? And that is very consistent with the train of thought. So therefore, we developed now a matrix for design acceptance criteria, right? Under this understanding that if you have more knowledge, therefore you have a lower spread, right, in that uncertainty, in those model uncertainty, and therefore you can be a little bit more aggressive with your designs. And this is what these matrices are showing you in terms of probabilities of failure and factors of safety. For a given economic consequence, let's say moderate, if you have low reliability in that design, maybe you should be targeting 5 to 10% probability of failure. But if you have very high reliability on that design, you know exactly how it's going to perform, you have very robust understanding, then maybe you can go much, much more aggressive because you're going to be able to take it economically, right? And you're monitoring pretty well. So you are sure you're going to be mobilizing all the people away if something starts failing. And same thing goes for factor of safety, right? So that has now become one option in the toolkit for an open pit operator, right? For when they see an opportunity to optimize design. The guidance in 2009, it's here, right? The moderate reliability here, as in 2009. And when you start on conceptual analysis, conceptual designs, that's where you should probably target, right? Because you're at a conceptual level, you're not there. But once you start operating, you need to judge yourself. Am I at the low, very low? And therefore I should be a little bit more conservative. But better yet, should I strive to go towards the higher design reliabilities so that I could actually optimize my designs, which would then allow me, right, to be more aggressive. So that's what we see this working. Now, we've developed this for open pits. This is not for tailing storage facilities. Why is it not for tailing storage facilities? Because of the very different risk profiles of these structures. In a typical open pit, and that's where engineering judgment comes into play, right? Are you having the typical open pit design profile? In a typical open pit, the open pit is very restricted to outside people, to third parties that don't have permission to go into the pit. Failure volumes are very constrained to the pit footprint, right? And we have the capacity for cleanup of the footprint. We have very robust and redundant monitoring tools and tarps so that we can see a failure coming, and we can, in a robust operation that understands their failure modes, of course, we can see a failure coming and we can mobilize equipment and people. In the case of the Bingham Canyon, they saw the failure coming, they mobilized equipment and people were taken out of the pit. The problem there was that it was misunderstood the entire volume of failure. So some equipment that was not mobilized out of the pit got damaged, but people were mobilized outside. Environmentally as well, right? Everything is constrained within the footprint of the pit, which can be cleaned up. On a tailings facility, on the other hand, if you have a loss of containment, you cannot mobilize the environment out. And as we've seen, unfortunately, in some of the cases in Brazil and lately other places in the world, it is very difficult to mobilize people, right, downstream. So it's a very different risk profile. So the treatment of these facilities has to be very different, right? Okay, so that's what I had for you today. I think we have 5 minutes to spare, if I'm correct. So I'm I'm here for questions for these 5 minutes. And thank you again for your attention. And thank you for letting me present this to you.
Thank you for the presentation. That was great. It's always great to see probability being integrated into rock mechanics and engineering. It's so important to consider because we just know so little, right? So I absolutely agree. Thanks a lot. So we have 3 questions in the chat or comments, I guess. Sharzad says, thanks, Renato. That was a great presentation. I have to get to another meeting. So that was that. Ed Siebritz asks, Renato, what do we know about what Bingham changed as a result of their slope failure? I would have expected it to already be carefully monitored and modeled. I guess you spoke about that a little bit.
Yeah, that is correct. I was not part of the team dealing with the failure. I do work closely with a Rio Tinto specialist, and there were a few changes, updates to, of course, monitoring and interpretation for sure, particularly because they discovered the potential for that particular fracture system to generate larger failure modes than what was anticipated. And in that regard, their TARPs would have had to be updated as well. But also their risk profile was updated as well. And so what do you do? Because now, in terms of moving people out of harm's way, it worked really well. But in terms of managing the economic consequences, that was a little bit more of a challenge, right? One of the many positive things actually that they did was that they got the regulator involved from the get-go. And on hindsight, that's what allowed them to actually mitigate the economic consequences pretty well because they had the regulator on board to clean this thing up and get operations running again, right? So the initial very steep investment in remotely operated equipment, investigations, etc., and getting experts from all over the world, et cetera, paid off because they were able to resume operations pretty shortly after. So that was a very nice lesson. The other one is this matrix here. They had to start looking at this from a reliability perspective, which not many people do, right? You just like get your results, your data, you build up a model, factor safety of 1.2 for this wall, away we go. They had to put reliability in it because that was the problem that they had. What was the reliability of their calculations of potential failure modes, failure volumes, right? So, and that's where this stemmed from. So now an update for the guidance is being moved. We're not going to change that table that I showed you at the beginning, but we're going to give you another tool, which is what I'm presenting you today. And that's stemmed from that operation, right, after the mana phase. So that's another positive storyline that came out from there. And if I remember correctly, they revisited the sequencing of excavation, particularly associated with slopes around that particular failure, to minimize the disturbance, stress relief, and mobilize potential material that could fall down if a failure occurs, such that failure volumes would not be as enormous as the one that they had at that time. So as you can understand, then the economic consequence gets reduced, right? So to my knowledge, those are some of the outcomes and some of the things that came out of it. There's probably more, yeah.
Thank you so much. Just a quick one, I guess. Jillian Noonan had a 2-part question. Are there any related references in the works by you or others that you would recommend to learn further on this topic? And the second part was specifically, will this work be included in the 2025 LOP guideline for open slope design?
That's a good question. With regards to publications, if you go to the proceedings for the 2022 slope stability in mining and civil that was in Arizona, we had a keynote lecture there with Rio Tinto that lays down extensively, not just this work, but how it fits together with the operator and the planner. I thought that was a beautiful keynote. And there's also a couple more papers by Ashley Creighton from Rio Tinto and by myself where we detail this work a little bit more. So those are really good. those are really good resources you can look at. And if you go towards a little bit more of how it started, there is the Canadian Institute of Mining journal, the CIM, and there's a paper there by myself and Ashley Creighton and Derek Martin. And we put the first part of the work that was done here. So there's been a few updates in our thinking, but that's the start of this work. And then you can contact me if you want for some of the research my students have been done in this aspect. We've published it in two journals about they've been looking at this epistemic uncertainty and try to do some quantification of part of it to see what's the role and trying to stress test these matrices. So there's been a few publications out there. And to the second part question, so Derek and oh my God, Mark Hawley, Derek Martin and Mark Hawley, they're leading this. I think that you probably were at their presentation maybe. And I'm one of the 3 leads for this chapter. And we are hoping that, as I said, this is going to be one of those tools available to you.
Thank you so much. I think we're over time. So once again, thank you so much for your time and for the presentation. Is wonderful.
Thank you. Thank you for the invitation.
Yeah.
I really enjoyed it. Yeah.
Yeah.
All right. And I'll see you.